Okay, so continuing on, just as a recap from in chapter 7, we're now looking at the concept of titrations. So titrations are utilizing a standard solution of defined known concentration to determine the concentration of a solution of unknown concentration. Titration fundamentally utilizes stoichiometry in the chemical equation to relate the quantities of known stock solution and our unknown solution. So acid-base titrations fundamentally utilize an acid-base reaction. Okay, in redox titrations, redox titrations fundamentally utilize, instead of an acid-base reaction, redox titrations utilize a known redox reaction between an oxidizing and a reducing agent. Now, once you have your balanced equation, titrations are handled using the same calculation steps. So fundamentally, all you need is your balanced acid-base or redox reaction. And once you have your balanced chemical equation, you can begin to manipulate your chemical equation and in turn utilize the chemical equation for stoichiometry calculations. Okay. So fundamentally, a key idea in acid-base titrations is this idea of the equivalence point. It's the point when both reagents are present in their stoichiometric ratio given by the chemical equation. So they're present in equal stoichiometric amounts. So for example, for an acid-base titration, the moles of acid would be equal to the moles of base times, and this little term here is our stoichiometric ratio. So at the equivalence point, the moles of acid are equal to the moles of base times the stoichiometric ratio of acid to base. Now, looking at the following equation, if we have sodium hydroxide reacting with sulfuric acid to give sodium sulfate and water, at the equivalence point, so this is at the equivalence point, we know that the moles of acid, in this case the moles of sulfuric acid, are equal to the moles of base, which are equal to the moles of sodium hydroxide. And now my question to all of you is, looking at our stoichiometric ratio, so looking at our stoichiometric ratio, how many moles of sulfuric acid react with how many moles of sodium hydroxide? What is our mole to mole ratio? What is our mole to mole ratio? 1 to 2, exactly right. And we get that from our chemical equation coefficients. And really do not forget your chemical equation, your stoichiometric coefficients. They're critical to titration problems. Okay, so let's now continue on and let's discuss a critical feature of acids and bases, and that we handle acids and bases as solutions. So we can figure out the moles of acid and base by taking the molarity times the volume. So now we have a relationship between the molarity and volume of an acidic solution reacting with the molarity and volume of a basic solution. And at the equivalence point, the moles of acid are equal to the moles of base times the stoichiometric ratio. Now, an interesting thing about acid-base titrations, titrations only look at the volume of acid or base solution dispensed. The total volume of solution or added water when mixing these reagents doesn't matter. The only thing we care about is how much acid solution did we add and what volume of our base solution did we add. Everything else is just extra. So you may say, well, how do we detect the moles of acid or base in solution? Well, we can't necessarily detect the moles of acid or base in solution directly. Instead, what we do is we detect the concentration of H+ protons or OH- hydroxides in solution using a pH indicator. Now, an indicator, and I'll use a colored pen for this, is a chemical compound that changes in color in response to changes in pH. So for example, we have a few common indicators that we use on a day-to-day basis. Probably the most common is the one on the right, which is phenolphthalein. So as you see, when the pH is 9 or greater, phenolphthalein changes to this bright pink color. So indicators correlate the pH to a color change. Okay, so that's how we can actually see changes in pH, and that allows us to assess the amount of acid or base in solution. Now, we have a technical term to describe the point at which the indicator changes color. It's known as the end point. And the end point occurs when we have a slight excess of acid or base present in our solution. So in this case, we added another drop to this titration. The phenolphthalein turns this bright pink color, and this bright pink color would correlate to our end point. It is the point or the volume added when our indicator changes color. Okay, now one way that we can describe titrations is utilizing titration curves. They show pH as a function of the volume of acid or base added. So let's look at a few examples of common titration curves and a few cases that we commonly see when performing titrations. So the first case is a strong acid, strong base titration. Okay, so we're titrating a strong acid or base with another strong acid or base. So a classic example of this is hydrochloric acid and sodium hydroxide. Both of these, we have a strong acid in terms of hydrochloric acid and a strong base in terms of sodium hydroxide. This reaction in turn generates water, which is neutral. So water is neutral and has a pH equal to 7 for pure neutral water. So as we perform our titration, we'll slowly, so in this case we are titrating sodium hydroxide with hydrochloric acid. So we start off with a basic solution, which means we have excess hydroxide. As we add hydrochloric acid, initially we don't see a large change in pH because we still have a lot of hydroxide excess. And as we approach the equivalence point, we see a rapid decrease in pH. And then at the end point, we have a pH that's around 7 because we've effectively reacted all of our hydrochloric acid and sodium hydroxide to yield water. If we add a slight excess of acid, so let's suppose we have a slight excess of acid, that in turn leads to our end point, where our indicator changes color. And that's what we can detect, and that's how we know that we've gotten very, very, very close to our equivalence point. So let's show how titration questions are phrased. How do we actually solve titration problems? So the key feature of a strong acid, strong base titration is that you end up with generally a neutral solution at the end of your titration. So let's look at the following example. In this case, we have 10 milliliters of sodium hydroxide solution of unknown concentration. So sodium hydroxide is our unknown, and we titrated it with a 1 molar solution of HCl to the endpoint. The titration required 9 milliliters of hydrochloric acid to reach the endpoint, and we're asked to calculate the concentration of the unknown sodium hydroxide solution. So let's first write out what we know. So we know, first and foremost, our chemical equation. Sodium hydroxide is reacting with hydrochloric acid to yield water and sodium chloride. Okay, perfect. Now that we have that chemical equation established, we'll be able to use this for stoichiometry. Okay, so now what we're going to do is we're going to take our balanced equation, and now we're going to write all of the information that we know about this problem. So we know, so our molarity of sodium hydroxide is our unknown. The volume of sodium hydroxide solution is 10 milliliters. The molarity of our HCl solution is 1 molar. The volume of HCl solution required to reach our endpoint is 9 milliliters. Okay, so we know that at the equivalence point, the molarity of sodium hydroxide times the volume of sodium hydroxide is equal to the molarity of HCl times the volume of HCl. And now it's really important that we respect the stoichiometric coefficient. And now my question to all of you is, how many moles of sodium hydroxide are needed to react with how many moles of hydrochloric acid? What is our mole to mole ratio in this chemical equation? 1 to 1. Okay, perfect. So now what we're going to do, is we're going to solve this equation for the molarity of sodium hydroxide, and that in turn gives us the molarity of hydrochloric acid times the volume of hydrochloric acid over the volume of sodium hydroxide times 1 over 1. So that gives us 1 molar times 9 milliliters over 10 milliliters. The volumes cancel, and we end up with a 0.9 molar sodium hydroxide solution for our unknown solution. Does this make sense to everyone so far? Does this make sense to everyone so far? Okay. So let's keep going. Let's keep going with this example. So next we're going to look at the titration of a strong acid with a strong base. Okay? Nothing much changes. Again, we generate water, which is neutral, pH equals 7 for a pure water solution. So this time, in this example, we are titrating hydrochloric acid with sodium hydroxide. We start with an acidic solution. which means we have excess H plus. As we add sodium hydroxide, our solution becomes more basic. At our equivalence point, which is very close to our endpoint, we're at a neutral solution. And our indicator region, our indicator would ideally change color when we have excess sodium hydroxide added. And the indicator is changing color in response to excess hydroxide. So it's exactly like our strong acid titration, except in reverse. So let's now look and see, and let's try to solve a problem where we titrate a strong acid solution with a strong base. So we take 5 milliliters of hydrochloric acid solution of unknown concentration, and we titrate it with a 0.15 molar solution of sodium hydroxide to the end point. The titration required 4 milliliters of sodium hydroxide to reach the end point. So let's try to calculate the concentration of the unknown sodium hydroxide solution. So let's take about 4 to 5 minutes to work through this example, and don't be shy to message me your proposed responses for the concentration of the unknown hydrochloric acid solution, as that's our unknown solution in this run, in the chat. So we titrated an unknown solution of hydrochloric acid with sodium hydroxide, and I'd like you to tell me, what is the concentration of that hydrochloric acid solution? And we'll discuss this example in about another 4 to 5 minutes. We already see a few responses in the chat. That's very good. And I would double check your calculation inputs for the response I see in the chat. And when in doubt, write out the full expression and then plug in the numbers. If you'd like, you can also type out how you inputted the numbers into the equation, just so that way I can double check your work. And we'll discuss this example in about another 3 to 4 minutes. I'd like to see a few responses in the chat, just so that way, I can get a sense of where the class is at with this concept, and if there are any questions that I can answer. So the responses I see in the chat look great so far. I would just and for the equation setup that I see in the chat, that looks perfect. Just make sure you're punching things in the calculator properly, and you should get the correct response. That calculation setup looks perfect. Let's spend about another 2 minutes on this example, and then we'll discuss. I'm starting to see a lot of reasonable responses for this problem in the chat. I just want to give every student the opportunity to work through the problem and then submit their proposed response for feedback. and we'll discuss this example momentarily. Okay, so let's discuss this example. So first and foremost, let's write out our balanced chemical equation. So we have hydrochloric acid reacting with sodium hydroxide to yield water and sodium chloride. Okay, now for the next stage of our process, we can see that our equation is in fact balanced. Always good to check that. Now we're going to list what we know. So the molarity of our hydrochloric acid solution is unknown. The volume of our hydrochloric acid solution is 5.0 milliliters. The molarity of our sodium hydroxide solution is 0.15 molar, and the volume of sodium hydroxide solution is 4.0 milliliters. Okay. So now what we're going to do is we're going to solve for the molarity of HCl. We know that the molarity of HCl at the equivalence point, which is approximated to our endpoint, the molarity of HCl times the volume of HCl is equal to the molarity of sodium hydroxide times the volume of sodium hydroxide times, and now this is really important, what is our stoichiometric ratio? What is our stoichiometric ratio? How many moles of HCl react with how many moles of sodium hydroxide? What is our mole to mole ratio? 1 to 1. Okay. So now that we have that set up, all we have to do is plug in our numbers. So the molarity of HCl is equal to the molarity of sodium hydroxide times the volume of sodium hydroxide over the volume of hydrochloric acid, which gives us 0.15 molar times 4 milliliters over 5 milliliters, which gives us 0.12 molar hydrochloric acid. Does this example make sense to everyone? Does this example make sense to everyone? Any questions on this example? If not, let's continue on and let's look next at weak acids and weak bases in titrations. So for example, if we're titrating acetic acid, which we know is a weak acid, with sodium hydroxide, which is a strong base, we generate acetate, which is a weak base, and water. So since acetate is a weak base, the pH at the end point, oops, one moment. Allow me 1 second to reset OneNote as it's experiencing a small amount of delay. Okay, perfect. So the main feature, because we have a weak base generated as our product, the pH at the end point will be greater than 7. So we will have a basic solution at the end point. Don't worry too much about that for now. It's just one quirk when you're titrating a weak acid. Likewise, when you titrate a weak bases generate conjugate acids that are slightly acidic, so that they change the pH at the equivalence and end points. So for example, ammonia, which is a weak base, when titrated with hydrochloric acid, which is a strong acid, yields ammonium. And of course, you end up with chloride as a byproduct as well. And ammonium is a weak acid. So that means our solution will have a pH less than 7 at the end point. Now, there's one other feature of weak acids and weak bases, is that weak acids and weak bases, when they react, they buffer the change in pH by reacting with the added strong acid or strong base to generate a weak conjugate acid or conjugate base. For example, if I look at ammonia, for example, if I have a solution of ammonia and I add some hydrochloric acid, I'll end up generating ammonium as well as water and chloride. In effect, what we have done is we have converted, using our buffer, we've taken a strong acid in our solution and we've reacted it to generate a weak conjugate acid of our buffer. So the way that weak acids and weak basic solutions mitigate changes in pH is by converting our strong acid via a reaction into a weak acid. And because a weak acid doesn't change the pH of our solution so much, when we try to titrate a weak acid or a weak base, we don't see pretty dramatic changes in pH all the way up until we reach our very close to our endpoint. Okay, so let's look at an example of a weak acid, strong base titration. So this time we're titrating acetic acid with sodium hydroxide to generate acetate and water. So at the equivalence point, or at our endpoint, our pH is greater than 7. You may notice that the region before the equivalence point is a lot broader, and that is known as the quote-unquote buffer zone, where the weak acid resists changes in pH by reacting the strong acid to generate a weak acid. Okay, so that's why our pH isn't changing substantially. In addition to the equivalence point, there is what's known as the half equivalence point. This is where our moles of acid are equal to our moles of base times the stoichiometric coefficients, which we'll call x over y. And because we're halfway to our equivalence point, because this is the half equivalence point, it's times 1/2. So they're present at half of their stoichiometric ratio. Okay, so let's keep going and let's look at what information we can derive from this problem. So graphically, if you're given a titration curve, we can actually read off a few things. So if we know that our equivalence point is here, we can first read off the pH at the equivalence point. We also can trace down into our chart and we can figure out the volume of sodium hydroxide at the equivalence point is equal to about 50 milliliters. We just extrapolated down to our x-axis in our plot. We also see that at the half equivalence point, the volume of our half equivalence point is equal to 25 milliliters. Okay. So from the graph, we can read off the volume at the equivalence and half equivalence point, as well as the pH at the equivalence point and half equivalence point. Now, just to get into some formal definitions here, the buffer zone is a region where the acid and its conjugate base are present in a 1:10 or 10:1 ratio. An addition of additional base or acid would result in a minimal change in pH. We call this solution a buffer solution. The half equivalence point is the point where the acid and conjugate base are present in equal concentrations. And one useful feature of the half equivalence point is that the pH at the half equivalence point is equal to the pKa of your weak acid. So you can get a lot more information when you titrate a weak acid. Now, let's keep things in perspective. Let's keep things in perspective here. And let's look at this titration in detail. So looking at our titration between a weak acid and a strong base, although there's a lot of information we can take in, fundamentally, the only thing that changes when you're dealing with a weak acid or a weak base is the pH of the equivalence point. The stoichiometry and the way that you handle the titration calculations stays the same. You only need to change the indicator. That's like a practical experimental modification. The calculations are exactly the same for a weak acid or a weak base titration. And I'm going to prove that to you. And we're going to look at the following example. So let's suppose we titrate 60 milliliters of acetic acid solution of unknown concentration, and we titrate it with 1 molar sodium hydroxide to the end point. The titration required 20 mils of sodium hydroxide to reach the end point, and we're asked to calculate the concentration of the unknown acetic acid solution. So fundamentally, just like before, we're going to write out our chemical equation. So acetic acid and sodium hydroxide react to give sodium acetate and water. And now from this balanced equation, we're going to write out what we know at the equivalence point. So at the equivalence point, which we're going to approximate to our end point, we know that the moles of acetic acid are equal to the moles of sodium hydroxide. And what is our stoichiometric ratio? What is our mole to mole ratio? How many moles of acetic acid react with how many moles of sodium hydroxide? 1 to 1, right? Exactly. So not much has changed from our hydrochloric acid titration example. Okay, so now what we're going to do is we're going to write out all the information that we know. So we know that the volume of acetic acid is 60 milliliters. The molarity of the acetic acid solution, we're not sure about. The molarity of sodium hydroxide is 1 molar, and the volume of sodium hydroxide is 20 milliliters. So then, solving our expression, we know that the molarity of acetic acid times the volume of acetic acid is equal to the molarity of sodium hydroxide times the volume of sodium hydroxide times 1/1. Now, plugging in some numbers to this, we're going to solve this equation, and we get the molarity of acetic acid is equal to the molarity of sodium hydroxide times the volume of sodium hydroxide over the volume of acetic acid times 1/1, which in turn gives us 1 molar sodium hydroxide times 20 mils over 60 mils, and that in turn gives us a molarity of acetic acid of, let me punch this into my calculator, 0.3 molar. Does this example make sense to everyone? Does it really matter a ton to our calculations, whether we're dealing with a strong acid or weak acid, or a strong base or weak base? Does it really affect our calculations at all? Did we do anything particularly different? Not really. The only thing that changes is practically we'd have to use a slightly different indicator. Okay, so let's keep going with this, and let's talk about something that's really critical to our understanding of titrations, and that really ties back to our idea of the chemical equation and stoichiometric ratios. So polyprotic acids can donate multiple equivalents of H+. So for example, sulfuric and carbonic acid, as we see, carbonic acid can donate 2 equivalents of H+. And as a result, it requires 2 sodium hydroxide molecules to react with it. Likewise, polyprotic bases can accept multiple equivalents of H+. Or you can also think of it as they can also, you can think of it as they're donating OH minus. So calcium hydroxide has 2 hydroxide equivalents, and as a result, in chemical reactions, it requires 2 equivalents of hydrochloric acid. Now, as we can clearly see from both of these chemical equations, the stoichiometry changes for polyprotic acids and bases. So let's look at some examples, and let's try to fill in. So if we look at oxalic acid, reacting with sodium hydroxide to give water, my question to all of you is, how many moles of oxalic acid react with how many moles of sodium hydroxide? What is our mole-to-mole ratio? What is our mole-to-mole ratio in this reaction? 1 to 2. Okay, so what that means is at the equivalence point, we see that the moles of sodium hydroxide are times this mole to mole ratio are equal to the moles of oxalic acid. We need to account for our reaction stoichiometry when we think about and we deal with titration questions. Okay. So let's look at another example. So let's suppose we're dealing with calcium hydroxide aqueous and we're titrating it with hydrochloric acid. Put the aqueous symbols in just for completeness to generate calcium chloride aqueous plus 2 equivalents of water. Now my question to all of you is, at the equivalence point, the moles of calcium hydroxide are equal to the moles of hydrochloric acid times, and now this is where we break out our stoichiometric ratio. How many moles of calcium hydroxide react with how many moles of hydrochloric acid? What is our mole to mole ratio? 1 to 2. Okay, perfect. So we recognize this idea that depending on our chemical reaction stoichiometry, the mole to mole, the amount of moles of each reactant in our titration will be different at the equivalence point. Okay. So when you think about titration curves for polyprotic acids and bases, so there are 2 protons, for example, for a polyprotic acid. So there are actually 2 equivalence points. So we have region 1, which is the first H plus being removed, and region 2, which is our second proton being removed. The second equivalence point is often the one that we care about the most. We typically overshoot the first equivalence point and we just ignore it in this class. We just titrate all the way to the second equivalence point or endpoint. Now, let's try to apply what we've learned to, and let's now discuss some intricacies of these equivalence points. The first equivalence point is the region where the acid and base are present in a 1-to-1 stoichiometric ratio, or in a stoichiometric ratio necessary to remove the first proton. The second equivalence point, it's the region where the acid and base are present in stoichiometric amounts, or in a stoichiometric ratio to remove the second proton. We typically care about the second equivalence point more. Okay, let's keep going. So looking at the following reaction between oxalic acid and sodium hydroxide, I'd like you to read through the following problem and then solve the following titration question. So for example, a 20 ml sample of oxalic acid required 20 milliliters of 0.5 molar sodium hydroxide to reach the endpoint. And I'd like you to calculate the concentration of the oxalic acid solution. So let's take about 4 to 5 minutes to work through this example. Don't be shy to message your proposed responses for the concentration of the oxalic acid solution in the chat, and we'll discuss in about 4 minutes. And we'll discuss this example momentarily in about another 3 to 4 minutes. So looking in the chat, I'm already seeing a few responses. Let me check. And the responses I see in the chat look perfect so far. And we'll discuss this example in approximately 2 to 3 minutes. Let's try to get a few more responses in the chat before we discuss. And we'll discuss this example in another minute and a half. Okay, so let's discuss this example. So first, as always, we write out our balanced chemical equation. Remember, stoichiometry is built upon a balanced chemical equation. Without it, it's almost impossible to, well, it's functionally impossible to solve these stoichiometry problems. Okay, so now that we have our balanced equation, we're going to write out what we know. So the molarity of our oxalic acid solution is unknown. The volume of our oxalic acid solution is 20 milliliters. The molarity of sodium hydroxide is 0.5 molar. And the volume of sodium hydroxide is 20 milliliters. Next, we're going to write out our equivalency at the equivalence point. So we know that the molarity of oxalic acid times the volume of oxalic acid is equal to the molarity of sodium hydroxide times the volume of sodium hydroxide. And now is where we break out our stoichiometric coefficient. How many moles of oxalic acid, how many moles of oxalic acid react with how many moles of sodium hydroxide? What is our mole to mole ratio? This is really important. What is the mole to mole ratio? 1 to 2, right? So then, once we have our mole to mole ratio established, what we're going to do is we're now just going to solve for the concentration of oxalic acid. That gives us the concentration of oxalic acid is equal to the molarity of sodium hydroxide times the volume of sodium hydroxide over the volume of oxalic acid times 1/2. If you forget the stoichiometric coefficient, your answer will be off substantially. So plugging this in, we get 0.5 molar times 20 milliliters over 20 milliliters times 1/2. And that in turn gives us 0.25 molar oxalic acid. Does this example make sense to everyone? Does this example make sense so far? Any questions on this example? Okay, so let's do another titration example, this time where we're asked to calculate some more features of our solution. This is where we're really looking now at titration reactions, neutralization reactions, and what else is going on at the end of our chemical reaction. So we have nitric acid reacting with barium hydroxide. So we have nitric acid, which is HNO3, reacting with barium hydroxide. Now, remember when I discussed acid-base reactions, I like to think about it in terms of H+ and hydroxide concentrations and equivalents. So barium hydroxide has 2 hydroxide equivalents. So to react with all of our hydroxide equivalents, how many H+ equivalents do we need? How many H+ equivalents do we need? And don't be shy to type your responses in the chat or to unmute and share your responses verbally. Two, yep, we need 2 H+ equivalents. So we need 2 equivalents of nitric acid. That in turn yields 2 water molecules. And then we take barium 2+ and nitrate, and we cross their charges to generate the formula of our salt, which is barium nitrate. Okay, so first question we're asked, what is the concentration of the barium hydroxide solution? So we know when we see the word neutralized, that is the amount required to reach the equivalence point. So we know at the equivalence point, the molarity of barium hydroxide times the volume of barium hydroxide is equal to the molarity of nitric acid times the volume of nitric acid times our stoichiometric ratio. And in this case, what is our mole to mole ratio? How many moles of barium hydroxide are required to react per mole of nitric acid? What is our mole to mole ratio? One to 1, 1 to 3, 1 to 2. What's our mole to mole ratio? 1 to 2. Perfect. So now what we can do is we can solve for the molarity of our barium hydroxide solution. Okay? So to accomplish this, we know the molarity of barium hydroxide is equal to the molarity of nitric acid times the volume of nitric acid over the volume of barium hydroxide times 1/2. And plugging in what we know, we see that the molarity of nitric acid is 0.15 molar. The volume of nitric acid is 50.0 milliliters. And then panning up, we see the volume of barium hydroxide to be 30 milliliters. And don't forget our stoichiometric coefficient of 1/2. And that in turn gives us the molarity of barium hydroxide to be equal to, let's punch this into our calculator now. So we have 0.15 times 50 over 30 divided by 2. That gives us a molarity of barium hydroxide of 0.125 mole. Okay, now we're also asked in the same question, we are asked to figure out what is the concentration of barium 2+ after the neutralization is complete. Okay, that's easy enough. Since this is a complete reaction, we know that the moles of barium hydroxide that we started out with is equal to the molarity of barium hydroxide times the volume. So then we have 0.125 moles of barium hydroxide per 1 liter. And we know that if we have 30 milliliters of our barium hydroxide solution, that is the same as saying, if we convert that milliliters to liters, that gives us 0.03 liters. Now, punching that into our calculator, we see that the moles of barium hydroxide are equal to 0.00375 moles of barium hydroxide. Now we know, looking as well at our chemical equation, which I'll write one more time. We know that at the end of our reaction, all of our barium hydroxide will convert to barium chloride, which will dissociate to barium. So we know that the moles of barium 2+ produced are equal to our moles of barium hydroxide. And now my question is, how many moles of barium 2+ are present per mole of barium hydroxide? What is our mole to mole ratio in this case? What is our mole to mole ratio? Looking at our formula, how many moles of barium are found per mole of barium hydroxide? One to one, exactly right. So we have 1 mole of barium 2 plus per 1 mole of barium hydroxide. So we know that our moles of barium 2 plus are 0.00375 moles of barium 2 plus. Now what we have to do is we have to look over at our, just one moment. Now what we have to do is we have to read through our chemical equation description, and we see that we combined 50 mils of nitric acid with 30 mils of barium hydroxide. So at the end of our reaction, allow one moment. Sorry about that. There's a small delay when moving across pages. Allow me to set us back to the page that we're on. So the key feature of this problem is that we have figured out the amount of barium 2 plus present at the end of the reaction. And now what we need to do is calculate the total volume of solution at the end of our reaction. So to do that, we know that our volume total is equal to 30 milliliters plus 50 milliliters, which gives us 80 milliliters, which will do us a favor and convert this to liters. And that in turn gives us the molarity of barium 2 plus of 0.00375 moles of barium 2 plus over 0.08 liters. And if we punch that into our calculator, that in turn gives us a molarity of 0.047 molar. So this is a bit of a combination between a neutralization problem and a dilution problem. Does this second part make sense to everyone? Does this second part make sense? If we wanted to figure out the concentration of barium at the end of our reaction, we calculate the moles of barium using our stoichiometry, and then we calculate the total volume, and we take moles over volume to get molarity. Does that make sense to everyone? Any questions on this example? Any questions on this example? So just to check that everyone's comfortable with this example, as I don't see any questions in the chat or verbally, let's try to work on the following problem solving session. And in this experiment, we took 20 mils of 0.15 molar phosphoric acid, and we neutralized it with 10 milliliters of sodium hydroxide solution. I'd like you to tell me at the end of the reaction, first, from this neutralization, what is the concentration of the sodium hydroxide solution? And second, what is the concentration of sodium plus after the neutralization is complete? So let's spend about 5 to 6 minutes on this example, and then we'll come together to discuss. Don't be shy to submit your responses for the proposed concentration of sodium hydroxide and the proposed concentration of sodium at the end of the reaction. Again, make sure you're paying attention to the stoichiometry. That's really critical for these titration problems. And we'll discuss this example in about 5 minutes. And again, don't hesitate to unmute and ask any questions that you have verbally. Don't be shy to also type your proposed responses in the chat, just so that way you can get a sense of where everyone's at so far on this question. So the response I see for the balanced equation in the chat looks perfect. That's a great place to start, with a balanced chemical equation. And now let's try to use that chemical equation in order to solve this neutralization problem. And we'll discuss this example in another 4 minutes. So checking the chat, let's see. And the response I see in the chat for the concentration of sodium hydroxide looks perfect. Let's try to get a few more responses in the chat, and we'll discuss this example in about another 3 minutes. And let's try to get a few more responses in the chat before we could discuss. And we'll discuss in about another 2.5 minutes. And the response I see in the chat for the concentration of sodium hydroxide looks perfect. Let's try to work now on figuring out the concentration of sodium after the reaction is complete. And we'll discuss in about another minute and a half to 2 minutes. Okay, so let's discuss this example once again, and let's work together on this example. So first and foremost, let's write out our balanced equation. So we have phosphoric acid reacting with sodium hydroxide, aqueous. Now, phosphoric acid donates 3 equivalents of H plus. So how many hydroxide molecules, how many sodium hydroxide molecules do we need? How many sodium hydroxide molecules do I need for a balanced equation? How many? 3, yep. That in turn gives us the following equation where we have sodium phosphate and 3 water molecules. Okay, to figure out the concentration of the NaOH solution, we know that the molarity of phosphoric acid times the volume of phosphoric acid times our mole to mole ratio, and let's figure that out right now. What is our mole to mole ratio? So my question is, how many moles of sodium hydroxide do we need per how many moles of phosphoric acid? What is our mole to mole ratio? Is it 1 to 1, 2 to 1, 3 to 1? What does our chemical equation indicate? Three to 1. Yep, looks good so far. Okay. Continuing on, we in turn know that the moles of phosphoric acid are equal to the moles of sodium hydroxide modified by our stoichiometric coefficient. So we have the molarity of sodium hydroxide times the volume of sodium hydroxide. So then, solving for the molarity of sodium hydroxide, we in turn get the molarity of phosphoric acid times the volume of phosphoric acid over the volume of sodium hydroxide times 3 to 1. And that in turn gives us the following. If we punch this into our calculator and we input our numbers, we see first and foremost, let me just pan up briefly, that the molarity of phosphoric acid is 0.15 molar. The volume of phosphoric acid is 20 milliliters, and the volume of sodium hydroxide is 10 milliliters. So then, Punching this into our calculator, we in turn get the molarity of sodium hydroxide is equal to, let's punch this into our calculator. That gives us a molarity, whoops, one moment, of 0.9 molar. Okay, now what we can do is we can take the molarity and volume of sodium hydroxide, convert it to the moles of sodium hydroxide, then we can convert it to the moles of sodium phosphate, and finally we can get the moles of sodium plus. This is to answer part 2 to figure out the concentration of sodium plus. So let's execute on this problem-solving scheme. So first and foremost, we know that if we have 10 milliliters of sodium hydroxide, I'll have to convert that to liters. We know that we have 0.9 moles of sodium hydroxide per every 1 liter. We can just go directly to the moles of sodium because sodium is a spectator ion. And my question to all of you is, how many moles of sodium plus do we have per mole of sodium hydroxide? What is our mole to mole ratio? What is our mole to mole ratio? How many moles of sodium plus do we have? 1 mole of sodium plus per every 1 mole of sodium hydroxide. Punching that now into our calculator, we have 10 times 0.9. That gives us 0.009 moles of sodium plus. Now, if we want to figure out the molarity, we're going to have to in turn convert and figure out our total volume. So our total volume in this case is our 20 milliliters of phosphoric acid plus our 10 milliliters of sodium hydroxide, which gives us 30 milliliters. And we're going to convert that 30 milliliters into liters to get us 0.03 liters. That in turn gives us the molarity of sodium plus. Molarity again is moles of solute over the liters of solution. And that gives us 0.009 moles of sodium plus over 0.03 liters. And that in turn gives us a 0.3 molar solution of sodium plus. Does this example make sense to everyone so far? Is everyone comfortable with this idea so far for these neutralization problems? These are staple acid-base neutralizations. You'll be doing a lot more of these neutralizations in later General Chemistry 2 courses. Any questions on this example? If not, let's move on to the next major subtopic in titration. In this case now, we are looking, instead of a normal acid-base reaction, what kind of reaction are we looking at in this next problem? It's really important that you're able to recognize what problem and what type of problem you're dealing with in order to effectively solve these different titration problems. So looking at the following reaction, just as your first impression, what type of reaction is this? Is this an acid-base reaction or is this a redox reaction? Is this an acid-base or a redox reaction? Do we have H plus and OH minus being exchanged? Is this an acid base or a redox? Exactly right, it's a redox. So let's just showcase this. So we're going from iodine 0 to iodine -1. We're going from sulfur, so this is +1, -2. So sulfur, we have -2 times 3 plus 2 over 2. So we're going from sulfur +2 to sulfur -12 plus 2 over 4 of sulfur of +2.5 oxidation number. Okay, so this is a redox reaction. So we're going to have to balance it utilizing half reactions. So we have iodine going to iodide. We're just going to balance this with respect to atoms first and foremost. Now we can count electrons. We have a zero oxidation number for iodine, a -1 for iodide. Our delta is going to be -1 over 0, which is 1 electron gained per iodine atom. And we see we have 2 iodine atoms. That gives us 2 electrons gained. Okay, so our first redox reaction looks good. Let's look at our second redox reaction. So we have NaS2O3 leading to Na2S4O6 plus 2 sodium plus. So now looking at our redox equation, we can clearly see from our previous assignments, we go from sulfur +2 to +2.5. Our delta is 2.5. So let me give it some more space. Our delta is 2.5 minus 2, which is 0.5 per sulfur. And we see that we have 4 sulfurs. Now, before we even think about this 4 sulfur counting, we need to balance this equation. So we have 4 sulfurs on the right, we have 2 sulfurs on the left, so we put a coefficient of 2. So that in turn gives us 2 electrons lost total. So we put our 2 electrons lost on the right-hand side. We see that we can now add our equations together, and that gives us the following balanced equation. So our electrons cancel. That gives us 2 sodium thiosulfate plus iodine leads to 2 iodide plus sodium, this thiosulfate dimer, plus 2 sodium plus. So now that we have the balanced chemical equation, we can begin to utilize our titration methods. So all of that work was just to get our balanced equation. And once we have our balanced equation, the calculations for redox titrations are exactly the same as acid-base titrations. So let's demonstrate that. So let's write down our volumes. Okay, so we have a 15 milliliter sample of iodine titrated with 0.1 molar sodium thiosulfate, and we needed 16.5 milliliters of sodium thiosulfate to reach the endpoint. So let's write down these numbers. So we know that our volume of iodine solution, so our volume of iodine solution is 15 milliliters. The molarity of our iodine solution is unknown. The volume of sodium thiosulfate solution is 16.5 milliliters. And the molarity of our sodium thiosulfate solution is equal to 0.1 molar. Okay, so now that we have all of this information in hand, what we're going to do is we're going to solve for the molarity of iodine, and that in turn gives us the molarity of iodine times the volume of iodine is equal to the molarity of sodium thiosulfate times the volume of sodium thiosulfate times our mole to mole ratio. And looking at our mole to mole ratio, how many moles of iodine react with how many moles of thiosulfate? What is our mole to mole ratio? So now that we've spent all this trouble getting our balanced chemical equation, what is the mole to mole ratio that we read off from our chemical equation? What's the ratio of iodine to thiosulfate? And this is where you'll see that once you have the balanced equation, you handle all titrations the same. Well, look, what's the coefficient in front of iodine, I2? The coefficient in front of I2 is 1, and the coefficient in front of thiosulfate is 2. So it's just a 1-to-2 ratio. Exactly right, exactly right. So now the molarity of iodine is equal to the molarity of thiosulfate times the volume of thiosulfate over the volume of iodine times 1/2. That in turn gives us 0.1 molar times 16.5 milliliters times 1/2 over 15.00 milliliters. And if we punch this into our calculator, and we're really careful with how we enter things into our calculator, we get 0.055 molar iodine solution. So that's our final answer for this problem. Does this make sense to everyone so far? Does this make sense to everyone so far? Any questions so far on any of these examples? As we see, the way that we handle redox titrations is exactly identical to the way that we handle acid-base titrations, except the way that you actually get your balanced equation is a little more involved. You have to balance the redox reaction. Any other questions on this example before we continue on? Any other questions on this example before we continue on? Okay, so let's continue on now and let's look at another problem. So in this case, we're looking at the following titration problem. We have 17 milliliters of potassium permanganate, and we're titrating it with 0.05 molar potassium oxalate, and required 10 milliliters of potassium oxalate to reach the end point. Let me write out the skeleton redox reaction. So we have permanganate reacting with potassium oxalate, and in turn we generate carbon dioxide gas, manganese 2 plus, and potassium, among other products. Now, what I want you to do is I'd like you to identify the oxidizing and reducing agents, and I'd like you to balance and write out your preliminary balanced redox reaction under acidic conditions. So let's focus first and foremost about getting a balanced equation under acidic conditions. So let's take a few minutes and we'll discuss the balanced redox reaction in about 4 to 5 minutes. So this is your prototype redox equation, and I'd like you to balance this redox reaction. And just as a note, we may have already balanced this redox reaction in an earlier example. So let's try to propose a balanced equation for this redox reaction, and we'll discuss this example in about another 3 minutes. Just first and foremost, let's get a balanced chemical equation. And don't be shy to message your balanced redox reaction in the chat. And we'll discuss balancing this redox reaction in another 2 minutes. And if anyone would like to propose a balanced equation for this reaction, don't be shy to type your balanced equation in the chat. Okay, so let's discuss this example. So first and foremost, let's assign oxidation numbers. So manganese, so solving for the oxidation number of manganese, we have -2 for oxygen times 4 for the 4 oxygen atoms plus 1 for potassium over the 1 for manganese. That gives us an oxidation number for manganese of +7. For carbon, we have -2 for oxygen times 4 plus 2 times 1 for the 2 potassiums over this time 2. That gives us an oxidation number of carbon of +3. In carbon dioxide, carbon is -2 times 2 over 1, which gives us an oxidation number for carbon of +4. For manganese, we have an oxidation number of +2. Oops, one moment. Allow me 1 second just to reset our view. Okay, so now that we have each of our half reactions prepared, or each of our oxidation numbers assigned, we're next going to set up our half reactions. So if we have potassium permanganate aqueous, that's going to manganese 2 plus potassium plus. Now, I'm going to tell you a little bit of a trick for redox titrations. You don't actually have to balance every single chemical species. You only have to balance the oxidizing and reducing agents in practice. But for this demonstrative example, we're going to balance this entire equation from start to finish. So we're going from manganese +7 to +2. Manganese is balanced, so we're losing for our delta. We have 5 minus, sorry, that was a bit of a slip up. We have 7 minus 2, that gives us +5. I could always get ahead of myself here. So we're gaining 5 electrons. Better way to write this would be final minus initial. 2 minus 7 gives us -5. That tells us we have 5 electrons gained. Okay. Now this equation isn't actually balanced as written. We have 4 oxygens on the left, so we need to add 4 waters to get 4 oxygens on the right. Okay, so now that we have 4 oxygens on the right, our next order of business is to balance hydrogen. So now we have 8 hydrogens on the right. Allow me 1 second. I'm noticing a delay in OneNote, so I'm just going to reset it really quickly. Allow me one moment. Allow me 1 moment just to reset OneNote, and then we'll be continuing on where we left off. Just 1 second. Okay, so as we discussed, we're continuing on and we're balancing each of our redox half reactions. We balanced out our main atom, manganese, and we counted that we had 5 electrons gained. Now we balance oxygen by adding water to each side, and now we're going to balance hydrogen by adding H plus to each side. So we have 8H plus on the right, so we're going to add 8H plus to the left. So now we have our complete and balanced half reaction, and we're going to repeat this process for our oxalate reaction. So in this case, we have potassium oxalate. So potassium oxalate is going to react to generate carbon dioxide as well as potassium plus. So our first order of business is to balance all of our non-hydrogen and oxygen atoms. So I see we have 2 potassium, 2 carbon, and 4 oxygen on the left. And we have 1 carbon, 2 oxygen, and 1 potassium on the right. So then, what coefficient do we need for potassium? What times 1 would give us 2? What coefficient do we need for potassium? Two. Okay, perfect. Likewise, we have 1 carbon on the right, 2 carbons on the left. 1 times what would give us 2 carbons? What coefficient do we need for carbon dioxide? 2. Yep, exactly right. Okay, so now that we've balanced this equation, we can count some electrons, and we see very clearly we went from +3 to +4. So our delta is equal to 4 minus 3, which is 1 electron per carbon atom. We have 2 carbon atoms, so we have 2 electrons lost. So this would be +2 electrons. Now let's write our entire set of equations. Let's write our entire set of equations, and then let's try to add them together. So we have 8H plus 5 electrons plus KMnO4 aqueous leads to manganese 2 plus potassium plus 4 H2O. And then we have potassium oxalate, which is K2C2O4 aqueous, leads to 2 carbon dioxide plus 2 potassium plus 2 electrons. And now my question to all of you is, what is the smallest common multiple? What do I need to multiply each of my equations by in order to get a balanced chemical equation? In order to balance my electrons? What is the common number of shared electrons? What is the common number of electrons gained and lost? What's the common number of electrons between both of these reactions? And don't be shy to type it in the chat or to unmute and provide your response verbally. 10 is exactly right. 5 times 2 would give us 10. So we're going to multiply each of our equations and then add them together. So that in turn gives us, at the end of this entire process, we have 16H plus, the electrons cancel, plus 2 potassium permanganate, plus 5 potassium oxalate, leads to 10 carbon dioxide plus 2 manganese, plus 2 manganese 2 plus 12 potassium plus 8 water. Now, here's a trick. Here's something really important. If you're only So if you're only going to use this chemical equation to relate the quantities of your oxidizing and reducing agent, if you're good at counting electrons, this set of numbers, this set of numbers to get the common number of electrons is a proxy for your mole to mole ratio of each of your two oxidizing and reducing agents. So we'll see actually when we solve out this redox titration problem that the ratio of your oxidizing agent of permanganate to your reducing agent of potassium oxalate will be 2 to 5. Redox equations fundamentally are built and balanced based on the number of electrons. So we have our balanced equation. So now we're ready to actually do this titration problem. To answer the question in the chat, I see in the chat the first question was, for the first half reaction, why do you use manganese 2+ for the charge and not potassium plus? So remember that when we're counting electrons gained and lost, we're looking at changes in oxidation number, changes in theoretical charge. If we look at potassium in detail, potassium stays +1 throughout the reaction. It's just a spectator that we use to ensure atoms are balanced. Manganese changes in oxidation number, so we care about how much did that oxidation number change, because that determines the number of electrons gained or lost. Okay, so now what we're going to do is we're going to write down all of the information that we have from our titration. We have our equation. Now let's write down all of this information that we have from our titration. So I'm going to rewrite my equation. Because 10 plus 2 would give us 12. I just added up the two potassiums on the right-hand side. Let me show that. So we have 2 plus 10, and that gives us 12 potassium. If you happen to not have the potassium balanced, it actually won't affect your answer in this case. And I'm really trying to get everyone to focus in on, if we're dealing with a titration problem, we care about the ratio of our oxidizing agent to reducing agent. If you get that right, if you have your electron counting right, this problem will work out perfectly. And that can let you save time, because if you're given a titration problem for a redox titration, you don't have to get your entire equation 100% perfect. You just need this ratio of your oxidizing agent to reducing agent. So it really can help if you're going through and you are pressed for time. Okay, so let's write down the information that we know. We have 17 mils of permanganate. We have 0.05 molar potassium oxalate and 10.5 mils of potassium oxalate. So let's just write those down really quickly. Okay, let me just check that I've transferred everything properly. 17 mils of potassium permanganate, 0.05 molar potassium oxalate, and 10.5 milliliters of potassium oxalate. So now what I want you to do, given the following information, I'd like you to solve for the molarity of potassium permanganate based on the following data given for the titration of potassium permanganate. with potassium oxalate. And we'll discuss this example in approximately 4 minutes. So now that we have our balanced equation, it's just a typical titration. And don't be shy to submit your responses via the chat or unmute and communicate your responses verbally. And if you have any questions, don't be shy to ask them verbally or in the chat. And we'll discuss this example in another 3 to 4 minutes. And I'd like to see a few responses in the chat with a few proposed solved concentrations of potassium permanganate. And we'll discuss this example momentarily. And the response I see in the chat looks good, but if you can add one more sig fig to that, just so I can check the accuracy of your response, but it looks good. It looks good so far. And yes, you did round it to the correct number of sig figs, but if you can just add one more sig fig just so I can check that the raw number is calculated correct. Yep, that's perfect. Exactly right. So one of the responses I see in the chat looks perfect. Let's spend about another 1.5 minutes on this example, and then we'll discuss. Okay, so let's discuss this example. So at the equivalence point, the molarity of potassium permanganate times the volume of potassium permanganate is equal to the molarity of potassium oxalate times the volume of potassium oxalate. And now is where we break out the stoichiometric coefficient. Now is where we break out the stoichiometric coefficient. And so how many moles of permanganate? Just one moment. Let me just move the chat box out of the way. So we have how many moles of potassium permanganate do we have per mole of potassium oxalate? What is our mole to mole ratio? Just reading off from our chemical equation, just like always, just like if we did an acid-base titration, what is our mole to mole ratio of potassium permanganate to potassium oxalate? 2 to 5. So really, once you have a balanced equation, you could do titrations using any reaction you potentially want, as long as you can detect the endpoint. This reaction is quite fun, as the solution changes color as you titrate it. Self-indicating per se. Okay, so solving, we get the molarity of potassium permanganate is equal to the molarity of potassium oxalate times the volume of potassium oxalate over the volume of potassium permanganate. Times 2 over 5. And now punching this into our calculator, we'd have the molarity of potassium permanganate is equal to 0.05 molar times 10.5 milliliters over 17 milliliters times 2 over 5. And that in turn gives us 0.012 molar potassium permanganate that we round to 0.01 molar following sig-fig rules. Does this example make sense to everyone so far? Does this example make sense to everyone so far? Any questions so far? Is everyone feeling confident with their ability to solve titration problems, including redox titrations? This skill will save you a lot in 102 when you have to do redox titrations and you're dealing with voltaic cells and other redox reactions. Any questions before we move on from this subclass of material? If not, let's keep moving on. And let's talk about combustion analysis. So this is a major tool that we have to determine empirical formulas and composition. And combustion analysis fundamentally is built on combustion reactions. So combustion analysis is a go-to method for determining the empirical formula of a compound using a combustion reaction. So for example, you have your sample and you expose it to excess oxygen gas under controlled conditions. That reaction then generates water and carbon dioxide, and the absorbers will pick up the water and carbon dioxide, and you can then weigh them to determine the mass of water and the mass of carbon dioxide generated from the combustion of a known mass of your sample. So, in order to help us understand how combustion reactions work, let's try to balance a few combustion reactions. So looking at C2H4 plus O2, again, we see a combustion reaction. That tells us we can use, looking at this isolated O2, we're going to be using half notation a lot. So in this case, we have 2 carbons on the left, we have 1 carbon on the right. So then, as a result, 1 times 2 would give us 2 carbons. Okay. We have 4 hydrogens on the left. We have 2 hydrogens on the right. 2 times 2 would give us 4 hydrogens. Adding up, we have a total of 4 oxygens plus 2 oxygens, and that gives us 6 oxygens. What times 2 would give us 6? We need a coefficient of 3. Now, although this may look a little bit unusual, you can also think about balancing chemical equations from a variable perspective. If you're curious how computers balance equations, they actually balance it using what's known as the algebraic method. Not so great if you're a human, but if you're a computer, the algebraic method works pretty well. So how does the algebra, how can we balance this equation if we have just variables? Well, if there are X carbons on the left, we'd have X carbon dioxide molecules. If there are Y hydrogens on the left, we'd have Y over 2 water molecules. And then for oxygen, we'd have 2X plus Y over 2, because that's our total number of oxygen atoms, over 2 for our coefficient of oxygen. So we can write out general balanced equations for any combustion reaction. That's pretty powerful stuff when you think about it. Let's do some more practice. And let's try to balance another type of combustion reaction. So looking at this next type of combustion reaction, we now have oxygen in our chemical formula. That's going to be a little bit problematic for us because if we have oxygen in our chemical formula, that in turn means we have to account for that oxygen atom when we're balancing this equation. So let's start with an example that we're comfortable with. I'd like you to take a few moments, let's take about 2 to 3 minutes, and let's balance this bottom chemical equation. So I'd like you to propose a balanced chemical equation for the following starred combustion reaction. And we'll discuss this balancing example in about 2 to 3 minutes. And the balance coefficients I see in the chat look great so far. So let's discuss. So in this equation, we have 2 carbons, 4 hydrogens on the left. Let's start with carbon and hydrogen first. So we put a 2 in front of carbon dioxide and a 2 in front of water. That gives us 2 carbons, 4 oxygens, 4 hydrogens, and 2 oxygens. So that gives us 6 oxygens total. So 1 plus what times 2 would give us 6. So in other words, what times 2 is equal to 5 oxygens? We have to guess a fraction. This is why half notation is so useful now, since we can guess a fraction of 5 over 2. And now what we do is we can multiply our entire equation by a common denominator of 2. And that in turn gives us the following balanced equation. 2C2H4O plus 5O2 gas leads to 4CO2 plus 4H2O. Now, we're starting to notice a bit of a pattern in combustion reactions, and don't worry, this exercise will have a payoff in a few moments. So if we wanted to think about this algebraically, again, we put an x and y over 2, and except this time for a coefficient for oxygen, we'd have x plus y over 2. We have 2x plus y over 2 minus z over 2 for our coefficient in front of oxygen. Now you may say, well, that seems like a lot of work, but I'd like you to try just in a moment to plug in your value of x, y, and z into this equation and see if we get the same half reaction equation. So you'll notice that although this method seems a little bit roundabout, it still is quite efficient at balancing chemical equations. And more importantly, this algebraic method of balancing provides us a general solution. Perfect. So now we can even add additional complexity and consider what would happen if we have nitrogen in our compound, in which case we'd make nitrogen dioxide. So we'll do this example really quickly just to showcase the elaboration of this idea. So if we have 2 carbons on the left, we put a 2 in front of carbon dioxide. If we have 4 hydrogens on the left, we need a 2 in front of water. 1 nitrogen, we put a 1. We have 4 oxygens plus 2 oxygens plus 2 oxygens, which in turn gives us 8 oxygens. 8 oxygens plus what? 8 oxygens is equal to 1 oxygen plus what times 2? So we'd guess a coefficient of 7 over 2. And now all we have to do is multiply this entire expression by 2 to give us our balanced equation. Again, when you're dealing with combustion reactions, you will really want to use half notation. It will save you so much time and so much hassle. Okay, so we've shown how to balance all the different types of combustion reactions. Okay, so what can we do with that? What can we do with that? Well, from balancing all of these different combustion reactions, we have a few key details that we picked up on. We see that if we compare carbon and carbon dioxide, all of the carbon dioxide generated came from the carbon in our original sample. So then we know the moles of carbon dioxide produced are equal to the moles of carbon in our starting material. There's no other source of carbon. We also know that the moles of water produced are equal to 1/2 the moles of hydrogen, right? Because all the hydrogen in our reactant ended up in water. And for nitrogen, the moles of nitrogen dioxide are equal to the moles of nitrogen in the starting material. Okay. Now, since excess oxygen is employed, our limiting reagent is the hydrocarbon. So all of our carbon dioxide, all of our water, all of our nitrogen dioxide comes from the carbon, hydrogen, and nitrogen in our sample. So now what we can do is in combustion analysis provides us the ratio of the moles of carbon dioxide, water, and nitrogen produced by combustion of the sample. This method alone does not allow us to calculate the molecular formula, but instead we can calculate our good old friend, the empirical formula. So if you have a sample of mass M total, combustion will give carbon dioxide, water, and nitrogen dioxide. And we know that all of our moles of carbon, so the moles of carbon in our reactant, are equal to the moles of carbon in carbon dioxide, which are equal to the moles of carbon dioxide. That's how we can get the moles of carbon by taking the mass of carbon dioxide over the molar mass times the mole ratio, which is 1:1. Likewise, we know that the moles of hydrogen in our reactant are equal to the moles of water times 2 moles of hydrogen per mole of water. Okay, that's where we get the mass of water over the molar mass times 2. And then finally, we know the moles of nitrogen are equal to the moles of nitrogen dioxide times 1 mole of nitrogen per 1 mole of nitrogen dioxide. Okay, so from this information, we can, from the mass of carbon dioxide, water, and nitrogen dioxide produced from combustion, we can calculate the moles of carbon, hydrogen, and nitrogen. And if we know the moles, we can certainly calculate the mole ratio. Okay, so let's keep going now because there's a bit of an elephant in the room here that we need to discuss. And that is, what about the moles of oxygen, right? Okay, now in combustion, so for example, if we're combusting something like methanol, the mass of oxygen in our products comes from the mass of oxygen in our reactant and also the ton of oxygen that we use for combustion. Okay, so clearly, can everyone agree that all of the oxygen in our products isn't just coming from our sample, right? We've reacted our sample with a large excess quantity of oxygen gas. And some of the oxygen atoms are incorporated into our products. So we're going to be a little bit clever and we're going to utilize the law of conservation of mass. And if we know the mass of all other elements in our original compound, and we know the total mass, the mass that we started out with, we can solve for the mass of oxygen. So if the total mass is the sum of the mass of all of our elements, we can solve for the mass of oxygen by taking our total mass minus the mass of each of our other elements. Now you may say, where do we get the mass? Well, just like always, we can calculate the mass of a sample by taking the moles of that element times its molar mass. Finally, once we have the mass of oxygen, we can calculate the moles of oxygen by taking the mass over the molar mass. Note, we're referring to atomic oxygen, not molecular oxygen. Now, once we have all of these moles, we can in turn determine the empirical formula using the methods previously covered in chapter 4. So once we have the moles, we can get the empirical formula, which is the mole-to-mole ratio. Now that's nice. Let's show how this works in practice. Let's show how this works in practice. So we have 8 grams of sample, and we're burning them to get 9 grams of water and 11 grams of carbon dioxide. Okay. So we're asked to calculate the empirical formula of the sample. So our goal is to figure out the moles of carbon, the moles of hydrogen, and the moles of oxygen in our sample. Okay. So then we can figure out that the moles of carbon, we're going to take 11 grams of carbon dioxide. We know that in 1 mole of carbon dioxide, we have 44 grams. And for combustion analysis, you want to make sure that your molar masses have been calculated correctly. If you make an error in any of these molar masses, it's going to be a pain later on because the numbers can vary and you want them to be as exact as possible. Okay, we also know we have 1 mole of carbon per every 1 mole of carbon dioxide. Okay. So punching this into our calculator, we have 11 over 44. That gives us 0.25 moles of carbon. Okay, we can calculate the moles of hydrogen. We have 9.0 grams of water. We know that we have 1 mole of water per every 18 grams. And we know that we have 2 moles of hydrogen per every 1 mole of water. Okay, so punching that in, that gives us 1.0 moles of hydrogen. Now, are we done? Can we just stop here and take our mole to mole ratio? Is there something that we may be missing? Is there something that we need to check for? Combustion analysis problems, you have to be very careful. And what do we have to pay attention for? What am I alluding to? What element do we have to check for in our sample? We have carbon, we have hydrogen. What do we have to check for as well? What element do we have to check for? Oxygen, yes, yes. So this is really important now. What we're going to do next is we're going to calculate the mass of carbon by taking our moles times our molar mass. So that in turn gives us 3 grams of carbon. And our mass of hydrogen, I always like calculating this because it's so easy. We have 1.0 moles of hydrogen times 1 gram per mole of hydrogen. That gives us a mass of hydrogen of 1 gram. Now, as we notice immediately, does 3 plus 1 equal 8? Do our masses add up to our total mass? No, and that implies we have some oxygen in our sample. So the mass of oxygen is our total mass, which is 8.0 grams, minus 3.0 grams, minus 1.0 grams, and that gives us 4.0 grams of oxygen. Now that we have the grams of oxygen, we can calculate the moles of oxygen by taking our 4.0 grams times 1 mole of oxygen over 16 grams, which gives us 0.25 moles of oxygen. Now that we have all of our moles and we've accounted for our total mass, what we're going to do next is we know that we have 0.25 moles of oxygen. We have 0.25 moles of carbon, and we have 1.0 moles of hydrogen. We have each of our moles in place, and now what we're going to do is we're going to divide by the smallest number of moles, in this case 0.25. Let's pick moles of oxygen. So that gives us 1 mole of oxygen per every 1 mole of oxygen. That gives us 1 mole of carbon per every 1 mole of oxygen. And then for hydrogen, oops, sorry about that. For hydrogen, when we divide by our smallest number of moles, that in turn gives us 4 moles of hydrogen per every 1 mole of oxygen. And that gives us, for our equation, CH4O. This is our calculated empirical formula. Does this look familiar to everyone? Does everyone remember this method of calculating empirical formulas all the way from chapter 4? Once we get the moles, does this make sense? Once we got the moles, does this look very familiar to everyone? Okay, so let's now try to apply what we've seen in this guided example to our own problem. So let's work on the following problem solving session. Given the mass of carbon dioxide and water generated and the total mass of your sample, I'd like you to calculate the empirical formula of our sample. And we'll discuss this example in about 5 minutes. And if you have any questions or if you'd like to propose a response for the empirical formula of the sample, don't be shy to let me know. And we'll discuss this example in about another 3 minutes. And don't be shy to submit your proposed response for the empirical formula of this sample. We'll discuss in about another 2 minutes. And if you have any questions at all, I'd like to see a few responses in the chat before we discuss, or at least some questions, just so that way I can help everyone as they work through these problems. Okay, so let's discuss this problem once again. So first and foremost, we can calculate the moles of carbon given the mass of carbon dioxide. So we have 0.3364 grams of carbon dioxide, and we know that we have 1 mole of carbon dioxide for every 44 grams. And we know that we have 1 mole of carbon for every 1 mole of carbon dioxide. Okay, so punching that into our calculator. That in turn gives us 0.00833 moles of carbon. To calculate the moles of hydrogen, we have 0.1500 grams of water. We know we have 1 mole of water for every 18 grams, and we know that we have 2 moles of hydrogen for every 1 mole of water, and that in turn gives us 0.0167 moles of hydrogen. We can then calculate the grams of carbon by taking our moles of carbon times the molar mass, which is 12 gram per mole of carbon, which gives us 0.1 grams of carbon. Our grams of hydrogen are equal to 0.16. Let me just check this really quickly. So we have 0.166. Let me check one more time.
I think there should be another 0.
At the end of which 0 point, there we go. That explains it. Perfect. So for our grams of hydrogen, we have 0.0167 grams of hydrogen. Okay, perfect. Now, obviously, both of these masses don't add up to 0.250. So let's calculate the grams of oxygen now. Oops, one moment. Allow me one moment just to reset OneNote. Sometimes it gets a little bit laggy when I share it via Zoom, but nothing that can't be fixed. Okay. Okay, perfect. So for our grams of oxygen, we're going to take our total mass, which is 0.2500 grams, minus the mass of carbon, which is 0.1 grams of carbon, minus the mass of hydrogen, which is 0.167 grams of hydrogen. And if we punch that into our calculator, we have 0.25 minus 0.1 minus 0.16. 0.25 minus 0.1 minus okay, so punching this into our calculator, we get 0.133 grams of oxygen. So now to calculate our moles of oxygen, we have 0.133 grams of oxygen times 1 mole of oxygen over 16 grams of oxygen. And that in turn gives us 0.00833 moles of oxygen. So now let's write out each of our moles. So we have 0.00833 moles of oxygen. We have 0.0167 moles of hydrogen, and we have 0.00833 moles of carbon. We're then going to divide by the smallest number of moles. In this case, let's just pick oxygen. We have 0.00833 moles of oxygen, 0.00833 moles of oxygen, 0.00833 moles of oxygen. And now when we punch this into our calculator, we have 1 mole of oxygen per mole of oxygen. We have 2 moles of hydrogen per 1 mole of oxygen. And we have 1 mole of carbon per 1 mole of oxygen. That in turn gives us a formula, empirical formula of CH2O, which is a common empirical formula for sugars such as glucose and sucrose, as well as the empirical formula for something like formaldehyde. Does this example make sense to everyone so far? Does this example make sense to everyone so far? Any questions so far? Can I get some responses in the chat just to get a sense of how everyone's feeling about these examples? Does it make sense so far? Okay, so let's do one last example to close out this lecture session. So Vanillin is a flavoring agent. It's made up of carbon, hydrogen, and oxygen. If you burn 2.5 grams of vanillin, you get 5.79 grams of carbon dioxide and 1.18 grams of water. So I'd like you to determine the empirical formula of vanillin. And we'll discuss this problem in about 5 minutes. So let's really try to make sure we're comfortable with these empirical formula calculations from combustion analysis, and then we'll discuss momentarily. And again, don't be shy to message in the chat your proposed responses for the empirical formula of vanillin in the chat. And we'll discuss this example in about another 3 minutes. And don't be shy to message your proposed response to the empirical formula of vanillin, and we'll discuss in about 2 minutes. And the response I see in the chat looks great so far. And we'll discuss this example in about another minute. Let's try to get a few more responses in the chat and then we'll discuss. And just remember that for empirical formulas, you need, when you're not to round and you want to multiply all of your subscripts by a common whole number to give whole number subscripts. So let's talk about this example now that we have a few responses. So to calculate the moles of carbon, we have 5.79 grams of carbon dioxide. We know we have 1 mole of carbon dioxide. So we have 1 mole of carbon dioxide per every 44 grams. And we know we have 1 mole of carbon for every 1 mole of carbon dioxide. And that in turn gives us 0.129 moles of carbon. For our moles of hydrogen, we have 1.18 grams of water. We know we have 1 mole of water per every 18 grams. And we have 2 moles of hydrogen per every 1 mole of water. So punching that in, that gives us 1.18 over 18 times 2. That gives us 0.1311 moles of hydrogen. Okay, and now finally for our, we need to calculate the mass. So the mass of carbon is 0.129 moles of carbon times 12 gram per mole of carbon. That in turn gives us 1.548 grams of carbon. Okay, so for our mass of hydrogen, we have 0.1311 moles of hydrogen, and we have 1 gram per 1 mole of hydrogen. That gives us 0.1311 grams of hydrogen. Finally, to calculate the mass of oxygen, we have 2.500 grams minus 1.548 minus 0.1311. And that in turn gives us, after we punch this into the calculator, 0.8209 grams of oxygen. Now that we have the mass of oxygen, we can calculate the moles of oxygen by taking 0.8209 moles of oxygen times, oh no, sorry, that's grams. So grams of oxygen times 1 mole of oxygen per 16 grams. That in turn gives us 0.0513 moles of oxygen. Now let's punch this into our calculator. So our moles of oxygen are 0.0513 moles of oxygen. Our moles of hydrogen are 0.01311 moles of hydrogen. And then our moles of carbon are 0.01298 moles of carbon. We're going to divide by the smallest number of moles, which is 0.0513 moles of oxygen. So punching this into our calculator, we in turn get 1 mole of oxygen per mole of oxygen. For this next set, we have 0.01311 over 0.013. That gives us 0.3069 moles of hydrogen per mole of oxygen. And for our moles of carbon, we have 0.01298 over 0.0513. That gives us 0.2530 moles of carbon per mole of oxygen. Okay, so now that we have our mole to mole ratios established, what we're going to do is we're now going to have to guess a reasonable set of coefficients. Let me re-enter and re-perform some of these calculations just to check the accuracy and just to make sure there are no major issues with the setup for this problem. So let me just punch things into my calculator one more time. 5.79 over 44. There was a calculator error here. This should be 0.1315 moles of carbon. For hydrogen, if things look odd, it's always best to just re-enter things into your calculator and just double check your calculations one more time. I know it seems steppy, but it'll save you a lot of grief. So just recomputing after we've double checked our calculations. And it's really important that when you go through that you make sure all of your numbers are 100% correct. So you may have to go through and just redo your calculations from scratch and just double check your calculations one more time. I'm just going through and cleaning up and correcting all of my numerical inputs. So that way my decimals are more accurate. So we have 0.0497 moles of oxygen. Now we punch that into our calculator and we take our mole to mole ratio. So we have 0.0497. Allow me one moment just to reset OneNote. Okay, perfect. It's back up. So we have 0.0497 moles of oxygen. So we're going to divide by the smallest number of moles, which is the moles of oxygen. We have a 1 mole of oxygen per every mole of oxygen. Now let's look at hydrogen. So we have 0.01311 moles of hydrogen over 0.0497 moles of oxygen. That gives us 0.264 moles of hydrogen per mole of oxygen. For our moles of carbon, we have 0.1315 moles of carbon over 0.0497 moles of oxygen. That gives us 0.264 moles of carbon per mole of oxygen. And now what we're going to do is we're going to have to guess. We're going to have to guess. We're going to have to find a whole number to multiply each of our coefficients by. We're going to have to find a whole number to multiply each of our coefficients by in order to give us non-zero numbers. Okay, so one thing from our initial examination is that we divide by the moles of oxygen. Let's instead divide by the moles of the smallest quantity, which in this case would be the moles of carbon or hydrogen, and let's see what we get as a result. So if we divide by 0.01311 moles of hydrogen, that in turn gives us, we have how many moles of oxygen per mole of hydrogen. So punching that into our calculator, we have 0.0497 over 0.01311. That gives us 3.79 moles of oxygen per mole of hydrogen. Okay, we have 1 mole So looking at our mole to mole ratios, in this problem, it's a little more tricky to get a clean mole to mole ratio. So what we're going to do first and foremost in terms of the setup for this, we can divide by the smallest number of moles, but then it gets a little bit trickier in terms of finding the correct whole number coefficient. So let's look at what happens if we divide by the moles of oxygen. So if we divide by 0.0497 moles of oxygen, we get 1 mole of oxygen per every mole of oxygen. We get 2.6 moles of hydrogen per mole of oxygen and 2.6 moles of carbon per mole of oxygen. Okay, now what whole number coefficient can we guess to convert each of these decimals into whole numbers? What whole number coefficient should we guess? Remember, 0.66 is about 2/3. So what whole number coefficient should we guess? What times 2.6 would give us a whole number? Well, this is technically 2.64. So we'd multiply all of our coefficients by 3. Okay, and that in turn gives us C8H8O3. So especially if the numbers aren't small whole numbers, you may have to play around and guess multiple different whole numbers. As a general rule, when you're carrying through the calculation for these combustion reactions, you want to minimize rounding whenever possible. And you want to make sure that you're multiplying all of your subscripts by the same whole number. Does that make sense? Does this look familiar from our discussion of the empirical formula chapter? Does this look familiar to everyone from chapter 4 when we solved for the empirical formula? Any questions on this example? So once we have the moles of oxygen, hydrogen, and carbon, we divided by the moles of one of our chemical species, and then we multiplied each of our subscripts by a common whole number to generate whole number subscripts. Sometimes you have to play a little bit of guesswork, but recognizing the common patterns of common decimals is invaluable. Just like empirical formula problems, it's equally invaluable in combustion problems. Any other questions on this example? Any other questions on this example? So a key takeaway as well, if you're stuck, you can also try dividing by the largest number of moles and then multiplying all your subscripts up. That's another method that can work, especially when the whole numbers are large. Can I get some responses in the chat just to see if everyone's comfortable with these sorts of problems? Any questions on these examples? This is the last example we have scheduled for this chapter and today, so I just want to make sure we're ending on a reasonable note. Any last minute questions for this lecture session? If not, let's stop the recording.